There are some things about how atoms behave that having a better understanding of our electron configurations will help us be able to understand. One of them is it works to help us understand why some metals behave as multivalent metals. The rule that we haven't discussed yet that is associated with this is that half full orbital shells or full orbital shells are sort of better than partially full orbital shells. So, for example, 3p3 is a little more stable or lower energy than 3p2 or 3p4. And similarly, 3p6 is more stable than 3p5. So the idea here is that half or full shells are a little more stable than partially full shells. The reason for this is pretty mathematically complicated, and I'm not going to get into it, but I'm just going to say it has to do with the idea that if these things are all spinning, if they all spin together in the right way, they can cancel out some of their energy or some of their spinning when you consider them as a total. That's as far as I'm going to say. In the end, that's the rule. So if we consider something like copper, keeping in mind that copper has 29 protons, or an atomic number of 29. And then we write out its electron configuration. What we're going to be able to see is why it might form a valence, or it might form a stable charge of +1 or +2. So Cu can be +1 or Cu can be +2. And the point of what we're doing here is we're going to say why it's able to do those two things. So its electron configuration, we'll have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d9. You can check that, but 2, 4, 10, 12, 18, 20, 29 electrons to go with this 29 protons. So this is neutral copper. Nothing has happened to this yet. I'm going to quickly represent this by an energy level diagram because I think it will also help to illustrate what I'm talking about. So I have my 1s shell, 2 electrons, my 2s shell, 2 electrons, my 2p shell with 6 electrons, my 3s electron, 2 3s electrons, my 3p electrons, my 4s electrons, and then in my 3D I have 9. So 1, 2, 4, 5, 6, 7, 8, 9. There you go. Okay, so that's an energy level diagram representing my copper. So the simplest way that this can form an ion without doing anything strange is that it can lose both of these electrons. If it does that, then that would form the +2 ion. But there's a secondary thing it can do instead. If it wants, instead of losing both of those electrons, it could promote one of those electrons to this 3D shell. By promoting that electron, we use the word promote because it's going to a higher energy level, so that should be unstable. But by promoting the electron, the 3D shell goes from 3D9 to 3D10, which is the full shell, which is a little more stable. If that happens, now here, Instead of having 2 electrons, I just have 1 electron. So instead of getting my ion of +2, I'd only lose 1 electron, and I'd form an ion of +1. So copper 2 plus occurs when no promotion occurs, and it loses both electrons. And copper 1 plus occurs when 1 electron is promoted to make 3d10, which is a little more stable than 3d9. And as a result, it only loses 1 electron. So that's nice. Our new model helps us understand why some of the multivalent atoms will take on the charges that they do. There's more complicated things going on here. This is just a nice simple example. If you go through and try and sort of use this logic for all of them, it'll work for some and it won't work for everyone. So don't get too carried away with it, but this is just one nice thing that can be explained with our new model.